In this video, we are going to really discover the method for finding limits analytically, and that means mathematically. So we won't have to build tables of numbers anymore and look at the pattern approaching a certain y value. We won't have to look at the graphs necessarily and sort of track the graphs approaching from either side. We have some mathematics that allow us to find the answer to these questions, especially when the function doesn't work at the very x value you're interested in. So let's take a look at that. The first thing I want to look at some functions that are very well behaved. Functions that are well behaved are functions that are continuous through x equals c. And in those particular functions, we don't really have to do a lot of work. So let's look at some continuous functions, and let's see how the limits can be discovered pretty readily. So this is section 1.3. Let's take a look at, for example, f of x being x squared. This is a very well-behaved continuous curve. There are no sharp corners, it's smooth, it's continuous, and if I were to go here to, let's say, x equals 1, let's answer a couple questions. First of all, what is the f of 1? Pretty straightforward, right? F of 1 is 1. So the coordinate here is 1, 1. Now let me ask a different question. What is the limit as x approaches 1 of my function? Now remember, graphically, you're supposed to approach from the left side, you're supposed to approach from the right side, and everyone needs to be in agreement. Well, if you're on this road, everybody thinks they're headed up to y equals 1. If you're on this road, everybody thinks they're headed down to y equals 1. There's perfect agreement. It turns out for this continuous curve, it's easy to get your limits. The limit as x approaches c is just f of c. So it couldn't be easier. So we don't have a lot to discuss about curves like that. If you have a well-behaved continuous curve, and we've got a lot of well-behaved continuous curves. We've got lines, we've got parabolas, we've got sine and cosine. So there's a lot of very good continuous curves, and if somebody asks you for a limit, I guess you can go right for that particular function value. Let's try a couple of these. So if I had f of x was 2x plus 4, and I said, what is the limit as x approaches 3 on this function, 2x plus 4? Because it's a continuous curve and there are no breaks at x equals 3, we can use what's called direct substitution. In fact, I would always recommend trying direct substitution as your first approach. And generally, if you get an answer, it's usually the right answer. So we plug our 3 in as we would into the function itself. We get 6 plus 4, and we get the answer, which is 10. And that's because the f of 3 is 10. Now, limits and function values only match with very nice, well-behaved curves. That's, again, we're at x equals c. We're nice and continuous through x equals c, and we're in agreement. The function value matches that question, where was I headed? There are certainly curves where this does not work, and we need to talk about that. So let's evaluate some very basic limits. Knowing that well-behaved curves, we can simply go for the actual output or function value. So starting off with the limit of a constant. Now this is my function right here. F of x equals b, y equals b. We know what that looks like, right? It's pretty boring. It's a flat line at y equals b. So it doesn't matter where you go in x. You're at y equals b all the time. If you directly substitute in, well, where's the x in here? There is no x. There's nowhere to substitute. So the answer is just b. I was headed to b. No matter where c is, from the left, from the right, it doesn't matter. So the function value and the limit are the same. So limit of a constant is pretty easy. What about the limit of this curve, y equals x? Y equals x looks like this. Nice linear curve. Well, now we do have a place where we can plug our x value in, right there. So plug in direct substitution, x becomes c. So basically what's happened here is, you see, we went to x equals c, which would of course produce y equals c. Now the point is there. However, the real question is, where were we headed? Well, take a look where we're headed. We're headed to y equals c. So again, this is really nice, and it works really well when the curve is continuous and well behaved like that. You can just simply plug the x value into the function, and the function value and the limit match. So far, so good. This also works for exponential functions. I'm sorry, not exponential functions, power functions. This is like x squared, x cubed, x to the fourth, x to the fifth. If you look at any of those curves, here's x to the 1, here's x squared, here's x cubed. You know, look at all of your polynomial power functions, and you'll notice that they are all very nice and well behaved. No breaks. They're all continuous. I guess that means I'm simply able to replace x with c as if I plugged it into the function, and I can get my limit that way. So I haven't done anything very fancy yet. All I've done is plugged the x value into the function. I did a function evaluation. So I'll say it again. The value of my function and the limit will be the same when functions are well behaved and continuous. And so far, that's all I've really looked at. Okay. Now, I want to look at some of the properties of limits. And many of these are common sense properties, by the way. Properties of limits. If I had a function when x approached c and the limit ended up being L, that's where we were headed for that function. I had a different function, maybe a g function. Same thing, we head for x approaching c, and that function, maybe that one approached a different y value. So here's two limits that we evaluated somehow, either graphically or numerically or ultimately analytically. I want to look at a couple of properties using these limits. What would the limit be as x approaches c of a scalar multiple multiplied by my function? Well, it turns out you can kind of think of factoring the b out front, if you would like, and simply evaluate the limit of this particular function, which we've already done. It's L. So I guess if there's a scalar multiple like that, scalar meaning some kind of quantity of value, you can actually factor it out front and then just evaluate this limit all by itself, which in this case turned out to be L. So b times L. This is for a scalar multiple. You can factor the b out front. Also, I want to be able to do sums and differences. So what if I said, can you give me the limit as x approaches c of, let's add the two functions together inside the limit, or subtract them, one or the other. You can almost think of this sum or difference with limits. You can almost think of using like a distributive law. You can distribute the limit to each function separately, like this. We do this limit all by itself, plus or minus, and we do this limit all by itself. Now again, in this particular example, we don't actually have to do the limits. They've already been done for us. So this limit was evaluated, became L, y equals L. This limit was evaluated, became K. However, we got there either graphically, numerically, or analytically. But you can see that the limit distributes through, and you can then just do each separately. And that's really a valuable property that we will employ. This also works for products. So if we took the two functions and multiplied them together, like this, you might say, well, I don't know what the limit of these two functions multiplied together is. In fact, that's a new function right there. But I certainly know the limit of each function independently, and maybe I can take advantage of that. Well, it's almost like another distributive law for limit. This is for products. the beauty of this is that each function gets its own limit symbol. So we do the limit on that one all by itself, and then later we do the limit on this function, and you can do them independently. We don't have to do it all together as one big function. Now remember, this limit was already evaluated as L, this limit was already evaluated as K, so we're actually able to compute that one as L times K. Okay, works for a quotient as well. If it works for products, it most likely works for quotients. So again, you might have a rational function where you divide these two functions like this. And you can think of distributing the limit to each of these separately. Now the beauty of that is that, well, remember, we already know the answer to that one, and we already know the answer to this one. This is for quotients, and it only works when k is not equal to 0, because otherwise it becomes undefined. And finally, for powers. What if I said, could you give me the limit as x approaches c of this function raised to a power? The function itself raised to a power. Well, in a sense, you can take that power out from the function itself and put it around the entire limit. And what's nice about that is you just have to take the limit of just a singular version of the function. Right here, remember, we know the answer to that. It's L. So these are some of the properties of limits. They're fairly common sense. You can distribute the limit through, and you can just deal with each function independently, and that is definitely a benefit. Okay. So let's actually look at a couple of limits. Now, I'm going to give you well-behaved functions, but let's try to use the properties to figure out the answer. Let's find the limit as x approaches 2 of 4x squared plus 2x plus 3. Hey, that's a sum. And if that's a sum, I can do each term separately. You more or less distribute the limit to each term. Now this right here is a product. So remember, you can actually pull these scalar multiples in front of the limit. Okay. One more. This is a power. Remember, this power applies to the x, but we have a little shortcut where we can make the power apply to the entire limit. So we kind of put the limit inside the squared now. So we just do the limit of x. Here's another limit of x. Let's finish it up. Now remember, we did this limit of x just a little while ago. That was one of our very basic limits. Check it out. The limit as x approaches c of x by substitution just becomes c, because we set x equal to c. You get x equals c. You get it right out. So this becomes 2. Just by direct substitution, it goes right in. This whole limit becomes a 2. This whole limit, same thing. The limit of x is just the x value itself. It's 2. But what's this limit right here? I want you to think about it for a second. Where do you plug x in? You don't. There is no place to plug x in. This is the limit of a constant. And look at the limit of a constant. It does not care what x is. A constant's a constant, and it stays that y value forever. So that's the same situation here. So what's our limit going to be? It's 4 times 4 plus 4 plus 3. So it's 16 plus 4 plus 3. The answer is, this limit's 23. So that's the answer to where we were headed. But because this is a parabola, because it's a quadratic, it's so well behaved that not only is this the answer to where were we headed, it's also the answer to what is the value of the function. So we don't have to go through that entire procedure. I just wanted you to see the properties of limits do work. But I always want you to try this first. Just try direct substitution. Let's try it. So the limit as x approaches 2 of 4x squared plus 2x plus 3, can we just get the answer quickly by actually just evaluating the function at x equals 2? We call that direct substitution. Watch what happens. Boy, this is much quicker. This is the way we're really going to do it. The answer is 23. There are so many problems that are literally that trivial. You directly substitute in, and the answer comes out. And we don't have to really do anything other than that. So where's the challenge in finding a limit analytically? Let me give you an example of a limit where direct substitution is failing. And I'll show you how it fails. I'd like to utilize this function right here, x squared minus 1 over x maybe minus 1. How's that? And I have two very important questions for you. The first question is, what is the f of 1? Let's find out. That's 1 squared minus 1 over 1 minus 1. 1 minus 1. That's 0. 1 minus 1 is 0. So without knowing anything about limits, this thing is undefined. In fact, it's so badly undefined, we call this the indeterminate form. Normally, divide by 0 means, well, it's undefined because it's infinite. But normally, 0 on top means the answer is 0. And normally, same over same means 1. In this case, it's none of those. It's just completely undefined. So f of 1 is undefined. We stop there. Now comes the question, what's the limit as x approaches 1? That's a different question. This says, yeah, I know, the function doesn't work. I don't care. Where were you headed anyway? Maybe the function was headed somewhere, blinked out of existence the very moment you wanted a result, and then went along its merry way. Just like that. And maybe this is x equals 1, and hiding over here is the answer I seek. Sorry. So I think that's probably what happened here. The function went undefined right there at x equals 1, but the answer to where I was headed does exist. We were headed to L when things stopped working. The question is, how am I going to get that value for L? So let's do this. We put the function in here and try direct substitution. We get 1 squared minus 1, 1 minus 1. Always try direct substitution first, and we get that. This brings up a very important point when you're evaluating limits analytically. When you evaluate a limit and you get the indeterminate form, do not say that the limit does not exist. In fact, I would recommend you say, I better dig deeper because there actually is an answer, I just don't know what it is. So anytime you get the indeterminate form, 0 over 0 we call that the indeterminate form. There's some other indeterminate forms out there too. Infinity over infinity is also an indeterminate form. Even 1 to the infinity power, strangely enough, is considered undefined or indeterminate. Whenever you get something that is one of these strange indeterminate forms, usually what's happening is the graph is blinking out of existence right where you want an answer. Does that mean the limit does not exist? Absolutely not. In fact, the limit very much does exist. It's just I don't know what it is. Here it is. It's L. So I need you to cross these off right away when you encounter them when you're calculating limits. This tells me to dig deeper. Always indicates dig deeper. So again, if you encounter the indeterminate form, do not tell me that the limit doesn't exist. In fact, the picture shows me that the limit very much does exist. It's just right where you want an answer. The function doesn't exist. I will accept that. but the limit definitely exists. Here it is, right here. From the left side, we're headed up to y equals L. From the right side, we're headed down to y equals, all roads lead to y equals L, but what is it? Well, I have a technique for you. It's called the dividing out technique. Let's look at that technique. What I want you to do is I want you to divide out. And what you are going to divide out, I'm going to refer to as the offending factor. So in order to do dividing out, I guess we need to know about factoring, first of all. And then what is this offending factor? The offending factor is the factor, the very one that's making the answer 0 over 0. And as soon as we get rid of that offending factor, all of a sudden the limit will emerge and give us an answer. So let's do a factoring exercise on this particular function, and let's divide out the offending one. So the limit as x approaches 1 of x squared minus 1 over x minus 1. First of all, let's just get this clear. It is not 0 over 0. That's a signal. That's a signal to dig deeper. Okay, how do we dig deeper? By dividing out the offending factor. Let's factor the numerator first. And then factor the denominator. Well, guess what, guys? There it is, the offending factor. In fact, put the 1 in here and you get 0. Put the 1 in there, you get 0. That's, of course, why we keep getting 0 over 0. But they're the same factor, so you can divide them out. So now we get a new limit. We get the limit as x approaches 1 of just simply x plus 1, a very well-behaved function that works using direct substitution. The answer here is 2. See, so limits have a role to play, and they don't always match the function value. In fact, when you get the indeterminate indeterminate form on a function, it's a signal to dig deeper and seek out that particular value, and the dividing out technique will get you there. Okay. Now there's another technique that I want to discuss, and that is called the rationalization technique. Anytime you get the indeterminate form, that's a signal. It says, there's an answer out there, and I need to go hunting for it. Let me show you how to do this one. This one has to do with radicals. So here's a question for you guys. The limit as x approaches 0 on the square root of x plus 1 minus 1 all over x. Fancy little function we've got here with a radical. Now, if you put, by direct substitution, x equals 0 in, look at what you get. You get the square root of 1 minus 1 all over 0. You get 0 over 0. Now, remember, if it's a limit, you cross that off immediately. You say, dig deeper. The problem with this one is, where's the offending factor? There's probably a factor in there that's causing me to get the 0 over 0. And the minute I take those factors out, the answer reveals itself. But how do you factor such a thing? You can't. So I'm going to show you how to find the offending factor. It's called the rationalization technique. Now, I think you probably remember that we don't like radicals in the denominator. That's true. In fact, to get rid of radicals in the denominator, we rationalize the denominator. This is actually simplest radical form. This is the form we prefer, but it's just not delivering the goods. So we're going to break the rules a little bit here. I'm going to put radicals in the denominator and hope that that alternative version gets me the thing I'm looking for, the answer, not this crazy 0 over 0 thing. So what we're going to do, guys, is rationalize the numerator. And the thing is, in order to do that, you have to remember the conjugate. Now, the conjugate for this numerator, remember the conjugate? It's an identical copy with a change in the middle. The conjugate here would be the square root of x plus 1, whatever that square root is, and then change the sign on the outside only, please. That's the conjugate. So what we're going to do is take this expression and multiply the top and the bottom by the conjugate. So let's put a conjugate up top here. Let's put a conjugate on the bottom. And here's how it's done. I really do want you to multiply the numerators together. I do not want you to multiply the denominators together. I realize you could, and I know you could distribute the x through, but it's only going to make things worse. I do need you to multiply the numerators together, and that would be a FOIL operation. So let's do the FOIL up there. Square root times a square root releases the contents. Now I have a plus 1 times a square root. I have a minus 1 times a square root. And I have a minus times a positive, and a 1 times a 1 makes 1. That's what I've got. Down below, I said, don't do it. It's tempting, but leave it alone. Now, what did this accomplish up here? Well, first of all, check this out. Plus and minus. And look at these. Plus and minus. Guess what we found? We found the offending factor. Pretty cool that it was hiding in there all along. We had to go digging for it. And here it is, right here. If you plug x equals 0 in, you get 0 here. If you plug x, there's the 0 over 0. So now you can use the dividing out technique and get rid of the offending factor. So you get the limit as x approaches 0 of 1, because there's a hidden 1 up there. And this is all left behind. Now let's actually do it and plug the 0 in. This is called direct substitution at this point. And if direct substitution yields an answer, it's probably the right answer, which is a half. So I've given you two very powerful techniques to find the answer to limits. The function values often don't pay off. They don't give us the answer. So you're going to have to dig deeper. When you get the indeterminate form, whether 0 over 0 or infinity over infinity, always signal that you want to dig deeper, and the way to do that is factor, divide out the offending factor, or in this case with the radical, it's a strange way to go because it was already in simplest radical form, but we do it anyway. We rationalize the numerator, and radicals end up on the bottom, I get that, but the offending factor comes out and reveals itself. Thank you very much, and we're going to move on to another video here in a moment, section 1.4. So when you have time to watch that one and take a look at the notes. And don't forget to be doing the homework and asking questions in class. And I will see you guys in class. Thanks.